Okay, welcome back to section 4.7. So this is the beginning of the class notes after that extreme value theorem handout. All right, so this is all about optimization. And I should tell you at the beginning that optimization consists of course, finding the maximum and minimum points, all right? But in addition, in calculus 3, we'll be finding saddle points because, well, they just show up, okay? And we can't just pretend like they're not there, okay? And also, in the second part, we'll do absolute maximum and absolute minimum points. And they're, again, entirely different processes or sort of different processes because one requires you to apply local arguments, right? Like the second derivative test. The other one, you just plug in a bunch of numbers to find absolute maxima and minima at the usual suspect points. All right, so look at this picture here. What I have drawn is f of xy, just to illustrate the point, right? You can tell that this is the highest point, okay? And so this is a local maximum. And yeah, let's say here's a point, you know, x naught, y naught, or xy here. And this is the point where the local maximum occurs, local maximum. And we say it's a local maximum because locally it's the highest point. You say, well, that looks like the highest point globally. Yeah, it may be, all right? And it may be a global or absolute maximum. And I'll just go ahead and write that because this is, as far as we can see in this picture, the absolute maximum. In other words, in this domain, it is the absolute maximum. But it's also a local maximum. Remember, it doesn't have to be one or the other. Local maximum simply means there is a small neighborhood or open set in which this is the highest point. That's all it means, okay? I'm not going to go into all the details of the definitions of local versus absolute, but local just means that there is an open set in which this is the highest point. And so that is local maximum as well as the absolute maximum. You see a point here that is a saddle point, okay? It is minimum going this way, maximum going this way, right? And so we will call that a saddle point and we will be able to find these, okay? In fact, we can't help but to find these. So erasing the eraser, this is also a local maximum. And this is a local minimum. And by the way, well, technically, when I talk about a maximum or minimum, I'm talking about the value, the z value, or f of xy. We could say this is where the local maximum occurs and give the xy coordinate, you know, as points. But anyway, that's what convention is. So if you are to find the local maximum, that means you're to evaluate the function at this point and give that z value. All right, so that's what we're trying to say here. And here's the definition. The first definition of what you need to see is this. If I'll explain something about the important things about local maxima and minimum later. But if f xy is given, okay, and we'll just call that z, right? Then x naught, y naught, okay, that's a point in the domain, is a, what do you think? Critical point. And the rest of this is as you expect. If the gradient at x naught, y naught, remember this is fx and fy, right? That's fx and fy, is equal to 0, 0, or undefined. Now, this can be undefined if one of these is undefined. Fx could be undefined, or fy could be undefined, or both could be undefined. And that would be a critical point. All right, so here's the fact. Not surprising, I'm sure. Right? In fact, let's call this facts. All right, every local extremum, every local maximum and minimum, and the saddle point occurs, guess what? At a critical point. Of course it does, right? In other words, you are looking for a point where fx and fy are both 0. Or sometimes, very unusual, sometimes they could be undefined, but not often because we typically work with differentiable functions in our calculus, especially in this class. All right, so those are the places you're going to be looking for. I call them the usual suspects because these are the usual suspects. You just have to investigate every time you are looking for an extremum, right? And number two, a critical point may or may not be any of these. Any extremum point. Okay, in other words, a subtle, local maximum, local minimum, none of these could be occurring. All right, so here's the picture. If you have a local maximum, okay, it's pretty obvious that here's a local maximum. If you go in the x direction or the y direction, the gradient, I mean, fx should be 0 and fy should be 0, right? And the same thing with the minimum point. Fx go this way, fy will go this way. And so because this is a minimum point, it should be, both of these should be 0. If you have a saddle point, I've done this before, but if you're coming in the x direction, it is the maximum, so the fx should be 0. If you're going the y direction, you're going, and this is the minimum point with respect to this curve, and so fy should be equal to 0. So everything I said here should make sense, right? And so really the point is, look for critical points if you're looking for any kind of interesting things like local maximum or local minimum, or saddle point. Number three, okay, now this is important. How do you know if it's a local max or local min or saddle point? Notice here, okay, now I'm going to say something very important here conceptually, right? Notice these look pretty much the same. You just, pick this one and put it upside down and you get this, right? This is very different because now we're talking about something that is a maximum in one direction and a minimum in the other direction. This also is called a surface of negative curvature. I know we don't talk about this type of curvature. I know we talked about a curvature before, but we are talking about a surface curvature. And this is what we call a hyperbolic surface. It has a negative curvature. I'm talking about what we call sectional curvature, which we will not study. But this looks like, these two look like the part of a sphere, like a ball. So imagine a baseball or soccer ball or basketball. They sort of look like a sphere, right? And every point, I mean, here's a maximum and there's a minimum, okay? And every ball, if you think of this as a z direction, every ball has a maximum and minimum. It's another one of those applications of the extreme value theorem. Okay, so you have absolute maximum and absolute minimum. All right, the saddle point is neither an absolute maximum, or a relative maximum, or local maximum, or local minimum. Okay, there is no way that you can find any open set where in which this is a maximum or minimum. Okay, because it is maximum in one direction and minimum in another direction. Right, so no saddle point can be considered a local maximum or minimum. It is a different beast all by itself. Okay, this beast has a saddle on top of it. So this is a very different thing. I just want you to know this is very different from this. Okay, so this second derivative test in calculus 3 is the one that distinguishes these two from this third one. All right, so we are going to define what we call D, the Hessian. What in the world is this? It's named for a person named Hess, and the Hessian is the value of fxx, fxy, fyx, fyy, the determinant of this 2x2 matrix defined at x naught, y naught. Now, obviously, this is fxx, fyy minus fyx and xy, fxy, but these are the same, remember? That's the theorem we learned. So this is called the Hessian, and we evaluate this at x naught, y naught. I know this is something different we haven't seen, right? But this Hessian actually determines or measures or helps measures what we call the sectional curvature I'm talking about. Remember I said the saddle point has a negative curvature and the spherical area. This is called the positive curvature. All right. And so here's how you decide this. All right. If D is negative, okay, then F has this means the surface is a negative curvature. All right. And this is a clear indication that if you have, oh, by the way, I'm assuming, suppose X naught, Y naught is a critical point. Okay. If you have a critical point, and if the Hessian is negative at that critical point, F has a saddle point. So the only way that Fx and Fy are 0 and Hessian is negative is if F has a saddle point at X naught, Y naught. So this is the last case. Okay, the negative curvature is what we talk about. If D is positive, then you have a positive curvature, and that refers to like locally, like a point on a sphere, like this. All right. So now we have to determine if it's positive, if it's maximum or minimum. Okay. Then, so how do you determine that? Well, if then we have to decide what this value is. Well, we know it's positive or negative, right? And if Fxx, this first thing, is negative, then F has a local maximum. And if Fxx is positive, that actually basically means it's concave up, right? Concave up like this. So F has a local minimum. So this resembles or reminds you of that second derivative test we just talked about, right? At this point, X naught, Y naught, right? So this is the famous second derivative test. You'll be using this over and over again in your assignment, right? So first define or find the Hessian at this point, capital D for the determinant. Find Hessian at this point. If that Hessian is negative, then you know it's a saddle point. If it's positive, okay, then look at this, you know, and say if that's positive. Oh, by the way, this part is always going to be negative, right? Because Fxy, whether it's positive or negative, if you square that, you will never get a negative number. So this minus Fxy square is most likely a negative number. So the point is, if Fxx is negative, or I would say if these are negative, okay, then definitely D is going to be negative. Okay. But Fxx actually has to do with you know, the second derivative in the x direction. So if you have this kind of an object here, as you come along from the, let's say here, as you come along from the back side to come on this side, you know, along the x direction, is the second derivative negative? If the second derivative is negative, that means you are going, like, it's a concave down, so you have a local maximum. And if Fxx is positive, that means concave up, and you're coming up like this. And so this is a local minimum, right? So that's the idea, right? And of course, if D is 0, then the test doesn't work. So the test fails. It doesn't tell you anything. Okay, so let's go ahead and do an example. And I don't have time to do a bunch of examples, but I think we can make this fairly clear. Just follow this for any problems where you are to find a local maxima, all the local maxima and local minima. The question will typically say something like this: find all local extrema. Remember, it's a plural word for extremum, and saddle points. Okay, because I mean, you will find all of them as you do this. For f of xy is equal to negative x cubed plus 4xy minus 2y squared plus 1. Okay, you may want to pause this a little bit, try to find the critical points, find the determinant or the Hessian, and see if you can apply the second derivative test to see which ones are local maximum and minimum and saddle point. Okay. All right, good. We'll come back. Here's the way to do this. You want to set fx and fy equal to 0, right? So this is negative 3x squared plus 4y, and that seems to be it, right? Because there's no x after that. For y, with respect to y, you have 4x minus 4y, and you want to set both of these equal to 0. Okay. So what do we have? Exactly. We have a system of not so linear equations. One is linear, the other is not. So system of equations, how do you solve this? Sometimes it is a system of linear equations. Sometimes it's more complicated like this. I think fortunately for this one, equation number two makes it easy, right? Because number two says, this tells you, an arrow means this implies that 4x is equal to 4y, basically saying y is equal to x. All right. So then you plug this fact into equation one. So you have to solve, and many times you will see for these extreme problems, you have to solve a system of linear equations because you have to set fx and fy both equal to 0. Right, now, if I know that x and y are equal to each other, I can just replace every y with x, right? So you have negative 3x squared plus 4x is equal to 0. You can factor out x, negative 3x plus 4 is equal to 0. And that means, remember, two things multiplied together is equal to 0 means one of them has to be equal to 0. So x is either 0 or 3/4. And so that's, oh, sorry, I think it's 4/3, isn't it? Yeah, 4 divided by 3. So those are the only choices. And of course, remember, x has to be equal to y, right? So the only critical values or critical points, the critical points are, and I should say maybe emphasize all critical points, okay, are 0, 0. Remember, x and y have to be equal to each other. And then 4/3, 4/3. Okay, now I cannot say 0, comma 4/3 or 4/3, comma 0, right? Because x and y have to be equal to each other. So I'm not saying x is 0 or x is 4/3 and y is 0 and y is 4/3. It has to be these two combinations of x and y. All right, so, oh, by the way, let's try to find the formula for D, right? So remember, this is fxx, fyy, fxy, fyx. Oh, by the way, when I say determinant, I hope you know the determinant of a 2x2 matrix is this times this minus this times that, right? So this is, now what's the second derivative of f with respect to x? That's negative 6x. And then fyy is negative 4, okay, minus fxy. So fxy is 4. And of course, fyx is also 4. So that, right? So this is 24x minus 16. That is the formula for that. Now you can plug in, if you d at 0, 0, of course you can plug in 0 here, is going to be negative 16. That's negative, okay? This tells you you have a saddle point at 0, 0. Now D, if you evaluate this at 4/3, 4/3, and it turns out y is irrelevant, what's x? If you plug in, 24 here, it's 24 times 4/3 minus 16. And that's, of course, this is, 8. So it's 32 minus 16, and that's 16, and that's positive. All right, what does positive mean? It does not mean maximum. It does not mean minimum yet, right? Because remember, if it's positive, it means it's a positive curvature. It may look like this or look like this. We have to determine which one. So in this case, the first one here, remember fxx, that turns out to be positive, no, that's, let's see, that's negative 6x, right? And negative 6 times 4/3 is clearly negative, okay? It's negative 8, yeah, okay. So it's clearly negative. And so this means, okay, remember, if the Hessian is positive, And if xx is negative, that means it has to be a local maximum. Again, let's not, the way you remember this, it may be confusing, but the way you remember this is just like the second derivative test in calculus 1. If it's if fxx is negative, that means you have this picture where the concavity in the x direction, going from back here to the front is concavity is down, which means, of course, it's local maximum. All right. And so, by the way, this tells you that f has no local minimum. Do you see why? You can say this with confidence. And that's because if there were a local minimum, okay, it has to happen at a critical point. Well, I know all the critical points, okay? In fact, there are only two of them. One's a saddle point, one's a local maximum. Therefore, there is no local minimum. This is very important for you to know. Okay, so in other words, if somebody says, look, I have discovered a very, very peculiar point. In fact, the point is when x is 20,500 and y is 30,000. At that point, you have and I found a local minimum. And you said, no, you didn't. Okay, you lied or you made a mistake, because I can prove with 100% confidence that there is absolutely no local minimum. How do I know that? Okay, just the same argument, right? Because this has to happen at a critical point. I happen to know all the critical points. There is no other critical point. And so that would guarantee that there is no local minimum. All right, so that's pretty much it, okay? And I will continue to look for maxima and minima, but I will try to do that in the context of absolute maxima and minima. And so let's pause here at this point, and maybe you can do a couple of examples, and then I will talk about the absolute maxima and minima in the next part of this video.